Hey everyone, and welcome. Today, we're cracking a really fascinating mathematical mystery. We're looking at a single, elegant equation that has, believe it or not, a whole bunch of secret identities. So, let's dive in and find out what they are.
So take a look at this. This is the general second-degree equation. And yeah, I know, at first glance it looks like a bit of a beast, right? But hidden inside this string of variables is the blueprint for a circle, an ellipse, a parabola, two lines crossing each other, and sometimes not even a shape at all, just a single point. So how on earth can one equation describe so many different things? Well, that's the puzzle we're going to solve today.
This right here is our main character. I like to call it the master equation. Think of it like a mathematical chameleon, because it's capable of changing its form completely based on just a few simple rules.
So how does it pull off this shape-shifting act? The secret, it turns out, lies in these 6 coefficients: A, B, C, F, G, and H. The best way to think about them is like ingredients in a recipe. Depending on the amounts you put in, you might bake a perfectly circular cake, or you might end up with something totally different like 2 crossed breadsticks. It's all in that recipe.
Okay, so how do we start decoding this recipe? Our investigation begins with our first major clue, our first decider, a special value that we call delta. This key is called delta, and it's the very first test we apply to our equation. Delta is going to tell us whether we're dealing with one of those famous conic sections you probably remember from school, or something else entirely, something a little stranger.
And here's how we actually figure out what delta is. It's the value of this 3 by 3 matrix, which is built right from the coefficients of our equation. Now, the first crucial step, the first big question we have to answer is simple. Does delta equal 0 or not? That one calculation is going to send us on 2 completely different paths. So let's explore that first path, which is full of surprises, by the way. This is what happens when delta is equal to 0. This is where our big, grand equation kind of collapses into simpler or what we call degenerate forms. So once we know delta is 0, we're not quite done. We need a second key to figure out what's going on in this world of collapsed shapes. We'll call this one little delta, and it's calculated with the super simple formula AB minus h squared. This little guy will tell us exactly which degenerate shape we're looking at. First up, what if our big delta is 0 and our second key, little delta, is positive? Well, in that case, the entire equation, with all its squares and all its variables, simplifies to define a single point. That's it. For instance, all that algebra on the left, just to define the tiny point 1, negative 2. Kind of amazing, right? Okay, next scenario. What if both big delta and little delta are 0? Then our shape-shifting equation transforms into the formula for 2 parallel lines. And in this example, the equation actually factors perfectly into the square of 2x minus y minus 1, which means you have 2 lines that are perfectly coincident, basically one line drawn right on top of the other.
And for our final collapse case, if big delta is 0, but little delta is negative, the equation literally splits into 2. It factors into the equations of 2 different straight lines that cross at a single point. So it's no longer one single curve, but 2 distinct lines hiding out in a single algebraic expression.
Now for the main event. We've seen what happens when our equation collapses. But what happens when delta is not 0? Well, now we leave the world of simple lines and points, and we enter the beautiful world of the true conic sections. And why are they called conic sections? Because every single one of these shapes, the circle, ellipse, parabola, and hyperbola, can be created by slicing a simple cone at different angles. A flat slice gives you a circle. An angled slice gives an ellipse, and so on. It's this really beautiful physical connection between algebra and geometry. So, to figure out which of these conic sections we have, we bring back our second key, little delta, calculated as AB minus h squared. This simple value is all we need to distinguish between these classic curves. And here are the rules. It's that straightforward. If little delta is 0, you've got a parabola. You know, think of the path a ball takes when you throw it. If it's positive, you have an ellipse, an oval shape. And if it's negative, you get a hyperbola, those cool twin curves. And a circle? Well, that's just a very special, perfectly symmetrical kind of ellipse. So, we've gathered all our clues, we've got our 2 keys, big delta and little delta. Let's put it all together into one complete guide. And here it is, the complete flowchart for identifying the shape hidden in any general second-degree equation. It's a simple 2-step process.
First, you check big delta. If it's 0, you look at the top half of the chart. If it's not 0, you look at the bottom half. Then, in both cases, you just use little delta to find your exact shape. It's an incredibly powerful and really elegant system.
And this really gets to the heart of it, doesn't it? It's not just about memorizing formulas. It's about seeing how a single compact mathematical sentence can contain so much possibility and describe so much of the world around us, from the orbits of planets to the shape of satellite dishes.
So the next time you see a complex equation, don't just see a jumble of symbols. See a mystery that's just waiting to be unlocked. I mean, if this one equation can be a point, a line, and a planet's orbit all at the same time, what other secrets are hiding out there in plain sight, just waiting for the right key?